So in this video, we will be looking at the colligative properties. Colligative properties. And so essentially, the presence of solute is going to give a solution different physical properties than the pure solvent would have. But in the case of these four important properties that you see on the screen, it's actually going to be the number of solute particles, not their chemical identity, that is going to make the difference. So again, it's important that you realize it is the number of particles present in the solution, not their identity, that is important. And so these colligative properties, these four properties here, are going to be boiling point elevation, freezing point depression, vapor pressure lowering, and osmotic pressure. And so most of these effects are going to be small, but they do have many applications, that many of which are actually vital for many organisms. But essentially in this video, we will be looking at boiling point elevation in more detail, and in the coming videos, we will explore freezing point depression, vapor pressure lowering, and osmotic pressure. All right, so now let's look at boiling point elevation in some more detail. So as the name would state, or as the name suggests rather, with boiling point elevation, we're saying how a solution boils at higher temperature than the pure solvent would. And so this colligative property results from the vapor pressure lowering. So we can say that the temperature of boiling, right, the boiling point, is going to increase as your concentration of solute increases. And again, this property is resulting from vapor pressure lowering. So let's look at this idea of vapor pressure decreasing in a bit more detail to get a better conceptual understanding of why we have an increase in boiling point for solutions as opposed to solvents, as opposed to pure solvents. So the fundamental reason for this is that, or for this lowering, is going to be involving entropy. Specifically, the relative change in entropy that is going to accompany vaporization of a solvent versus the vaporization of a solution. And so we know that a liquid vaporizes because gases have higher entropies than liquids. We know that entropy increases. Well, we know that gases have more entropy than liquids, which have more entropy than solids. And so naturally, liquids are going to try to vaporize to reach a state of higher entropy, and by being in the state of a gas. And so a liquid vaporizes again because there's a higher entropy in that state. And so in a closed container, vaporization is going to continue until the number of particles that are leaving and entering the liquid phase per unit time are equal. Or in other words, when your system reaches a state of equilibrium. And so, but as we said, right, the entropy of a solution is already higher than that of a pure solvent. Or in other words, water alone is going to have a lesser entropy than a solution of water plus, NaCl, for instance. And because of that, a fewer number of solvent particles are needed to vaporize to reach that same entropy. And so because of this, with fewer particles in the gas phase, the vapor above the solution has a lower pressure. So hopefully that's making some sense. But what does that have to do with boiling point elevation, you may ask? Well, if we remember the fact that the boiling point, if we call it T sub B, of a liquid is the temperature at which its vapor pressure equals the external pressure. So this boiling point is going to be the point when the vapor pressure is going to be equal to the external pressure. It's at this point that your liquid is going to start to boil. But the vapor pressure of a solution is going to be lower than that of a pure solvent. And so therefore, it's going to be lower than that external pressure at the given temperature, at that original boiling point of the solvent. And so then it doesn't boil. And so the boiling point elevation, this change in the boiling point, in other words, or more specifically, this increase in the boiling point results because a higher temperature is going to be needed to raise the solution's vapor pressure to equal the external pressure. And we're able to quantify exactly by how much our boiling point is going to increase using a handy little formula where we can see this change in boiling point is going to be equal to Kb times m times I. And so, well, what are each of these variables? Well, delta T sub B, that is the amount by which the boiling point increases. Our Kb is going to be the boiling point elevation constant. And that is a value that is dependent on the solvent. It varies from solvent to solvent. And so our Kb for water, for example, is going to be equal to about 0.512 degrees Celsius per kilogram over moles. M, or this lowercase m, is going to be the molality of the solution. And molality, not to be confused with molarity, is going to be equal to solute, or moles of solute per kilogram of solvent. This is going to be equal to this is what molality is. But if you remember, molarity is moles of solute per liters of solution. So it's important that you don't get these two mixed up. When we're looking at boiling point elevation, we're looking at molality, not molarity. And, well, there's actually a reason for that. The reason why, again, we use molality and not molarity is because molality depends on mass. We're looking at kilograms of solvent. And mass is something that doesn't change with temperature. Molarity, on the other hand, depends on volume, liters of solution. And volume is something that can expand or contract with temperature. And so that's why it would be unreliable to use here. So it's important that you realize we are using molality. And finally, this I. What is this I? I is the Van't Hoff factor. I is the Van't Hoff factor. And, well, what is the Van't Hoff factor? Well, let's just write it first. Van't Hoff factor. And, well, this is a number that represents the number of particles that the solute splits into in solution. And we realize that this is important because, as we talked about, boiling point elevation, this is a colligative property, and that is a colligative property is one that depends on the number of solute particles. Again, not the identity, but the number of solute particles. So, obviously, the number of particles is going to be important. And that's what this Van't Hoff factor is telling us. For example, we know that NaCl dissociates into Na plus and Cl minus. That is 2 ions. So the Van't Hoff factor for NaCl, this I, is going to be equal to 2. So now let's, we can keep these, what each of these values, represent in mind, and let's look at a simple example problem. So let's just clear this up before we look at our problem. All right, this is going to be simply to demonstrate a proof of concept here. We will be looking at more problems in another video that I'm going to make, where we're just going to be going through several different problems related to colligative properties. But here we'll just be generally demonstrating how to use the formula. So we're told, let's say that we dissolve 1 mole of NaCl in 1 kilogram of water. So let's start off by writing out our formula. That is delta Tb is going to be equal to Kb Mi. And, well, we know, let's try to identify, well, we already know what our Kb is for water. We remember that our Kb, K sub B, is 0.512 degrees Celsius, kilograms per mole. And what about our molality? Well, our molality we know to be moles per kilogram solvent. This is moles of solute. And well, in this case, we have 1 mole of NaCl per 1 kilogram of water. And so that gives us a 1 molal NaCl solution. So let's just clear this up a little bit. We can see that our M is then equal to 1. And what about our Van 't Hoff factor? Well, this is what we saw just previously before. We know that NaCl dissociates into Na plus and Cl minus. So that is 2 ions or 2 particles that this NaCl is going to dissociate into. And so our Van 't Hoff factor here is going to be equal to 2. And well, if we just take all of this information and plug it into our formula here, we can see that our delta T sub B, or our boiling point, is going to change by 0.512 times 1 times 2, which is equal to 1.024 degrees Celsius. And we get those degrees Celsius again because our units are, we're going to be basically doing kilograms per mole times moles kilogram, and so that units of kilograms and moles are going to cancel out, leaving us with degrees Celsius. And so this is our answer. But again, it depends on what their answer. Actually, in the question here, they weren't too specific about whether we were trying to find the amount by which our boiling point will change, in which case this would be our answer, or what our new boiling point would be. So let's find what the new boiling point would be. And so again, if they were asking by how much, this would just be our answer. But let's just try to find the new boiling point. We know water to have a boiling point of 100 degrees Celsius, pure water. But in this case, this solution is then going to have 100 degrees Celsius plus 1.024 degrees Celsius. And so now this solution is going to have a boiling point of 101.024 degrees Celsius. So this is going to be our new boiling point. So hopefully that is clear. This isn't something that's too complicated. Again, you just have to identify what each part of the formula would be from your problem, and then simply plug it in. So hopefully that made some sense, and if you found some value out of this video, be sure to check out the coming videos that explore the next 3 colligative properties. But if you like this video, please show your support by liking and subscribing. Again, leave in the comments if you have any questions, what you'd like to see next, and I'll see you guys in the next one.